Hi folks, so this is the last segment of Life Out There. And basically we've talked about characteristics for life, we've talked about the Drake equation, and we've also talked about sort of what things to look for. So now we're going to be concentrating more on presuming that there's intelligent life out there and getting into some more details of particularly about the SETI operation. And one of the first questions that we ought to ask are the ones shown here, and a little bit of snide remarks from me, if you will. But let me first talk about should we go there or not. Here is the current list of spacecraft that are leaving the solar system, which is a pretty big deal. But the point still being is that they're moving very, very slowly. Voyager 1 is the one that's going the quickest, and it's done a lot of things as far as teaching us or allowing us to measure objects in the distant solar system. And it is the one that's going the quickest, so it's going to go out there the furthest, and it's going to have a close encounter with this particular star, AC 793888, also called Gliese 445. in 40,000 years. Okay, it's going to get within 1.7 light years of it. But let me point out to you that that star is moving even quicker towards us now. It is approximately 18 light years from us right now, but in this close encounter that we're talking about in 40,000 years, it's going to be about a parsec away. So the star is moving even faster than this spacecraft is. And even though right now it's really, really far out there, it's the furthest one out there, it's going really dirt slow. It's a snail compared to stars out there. So our chances of actually getting out and visiting the solar system with our current technology is sort of not very likely. So let's put that away. Let's not even bother thinking about it. Now, on our spacecraft, we do have plaques and that sort of thing to indicate where we are. And one of my students has this tattooed on her back because she wants to become an astronaut, and so if she gets lost, she wants to be taken back to the Earth. So these are all indications of where Earth is, or our solar system is, relative to some pulsars in the neighborhood. So that's what these things are about. And we'll talk a little bit more about what you would put into a communication with an intelligent species out there, so that we can, so they can figure out where we're from, and we can figure out where they're from. I mean, the idea of codes and that sort of thing, and code breaking, is something that we would expect them to know as well as us. So, one of the other things about, I probably jumped the gun here, and that is, so should we go out there? And there are some projects and some studies that are being looked at. And going out there is not only us in some sort of generational spacecraft, although that's what some of these things are, like a 100-year starship. But there are also some things that are much different. So this breakthrough starshot basically would use laser sails, or like a solar sail, but it would be a spacecraft that's only a few grams in size. And so you can get some tremendous speeds out of that. These are things that you can look up on the internet and find out more information about it. I think this breakthrough starshot got a little bit of attention a few months ago. All right, so the next step is basically we really ought to spend our time either talking to these folks or listening to them. Probably not either or, but basically an and. I mean, obviously it is much easier and faster to just talk or listen rather than messing around with spacecraft. The message goes at the speed of light, but then the questions come up is, well, what do you say? How do you say it? Where do you point your communication device at? And how long do you point there? all these are important questions because, space is awfully big. And, you might think it's a long walk to the corner drugstore to go off the Hitchhiker's Guide to the Galaxy, but space is real big. I mean, it's real big. Now, we can talk about communications in a couple of different ways, and I'd like to do that. One is unintentional communications, and we've been out there with commercial radio for quite a few years in different types of modulation schemes, allowing us to send information on the band. And then we've also had TV for a while. The Olympics was first televised from Berlin in 1936, so the Contact movie did get it right in that regard, but it's unclear with the amount of signal power that they had that anybody would be able to detect it. But the same year, the BBC started regular programming too, so why they chose the Berlin Olympics to feed back to us in Contact rather than some BBC program is unclear to me. And then, only a few years later, they could have watched a baseball game. So what kind of frequencies should we use? Okay, this is just to remind you, we have light coming in all sorts of different flavors and colors. And we probably ought to use what's called the water hole, especially if we're trying to emit signals from the Earth rather than from space. We would have these issues of absorption of wavelengths or absorption of light going through gas clouds as well, or other atmospheres. So we need to be cognizant about this issue. So if we go too low in frequency, then the galactic background is just going to overwhelm us. And if we go to too high of a frequency, then we're going to be splitting atoms apart. So there's a nice hole here that is what we use for communication with our satellites in orbit to bounce back those signals back to Earth. Basically, we have C-band and K-band, which are like 3 to 4 gigahertz and 12 to 14. So in this region here and in this region here. So we would probably want to send scientific signals out in this region as well. Now there's another reason why, and that is this particular frequency is a good one because it's what is called forbidden. A forbidden signal is not absolutely forbidden, but in order to send a signal out, in order for a natural process to send a signal out at 21 centimeters or 1.5 gigahertz, it needs to be in cahoots with something else going on. It isn't a natural sort of thing to occur. Now, even though this is a picture, a special picture of the Milky Way, and we do see the evidence of the Milky Way here, and it's quite bright here. This is a lot less, this is pretty dim compared to other frequencies. So, the amount of energy that comparatively here is a lot less than other frequencies. Okay, so that's where we would want to go. It's more easily seen in this picture here. Okay. So what would you say in the message? Well, this is the message that was sent to M13, a globular cluster, and that was a mistake. But it was sent from Arecibo, and basically you would send them some mechanism of figuring out how you could decode a more complete message. Okay, so you would send them, numbers, and then you would send them some important things associated with, DNA and RNA, sugars and bases, again, using these numbers as a starting point. So if you remember in the movie Contact started with a repetition of base signals of prime numbers. So it was 1, then it was 2, then it was 3, then it was 5, then it was 7, and then it was 11, and it continued like that. And then the people looking at the signal in contact discovered more and more information as they started looking at what are called modulation bands. And first it was two-dimensional modulation, and then three-dimensional, until at some point they were able to decipher the entire message. So that's the sort of thing that you would do. You would start off small, going with the numbers, and then improving upon that, you would start creating, more complex messages within the message. Okay, and so when you sent it out, this is what it looked like. And so one could imagine that, you start off here and then you modulate this sort of thing on it, and then you just keep on going. Now, as I said, they sent it to M13, and M13 is a globular cluster. It's 25,000 light years away, so it's going to take quite a long time to get a reply. 50,000 years. Now, why is it a bad place? Well, here are a couple of pictures of it. Here's M13 with an 80 millimeter refractor. 80 millimeters is 8 centimeters, which is about 3 inches across. So this is not too big of a telescope. And you can see they're really pretty. This is the wrong color for it. It should be more gold in color. But when you look at it at the center of this thing with the Hubble Space Telescope, you look at all those stars there. You won't find any planets there because you're going to have a lot of stellar collisions. All those stars are just bouncing around. Well, they don't bounce off of each other. They're not like ping pong balls. They're more like pieces of clay. And, or say water balloons. And if a water balloon hits another water balloon, chances are it's going to break. And then if you've got planets going around these stars, they're going to get stripped off by any close encounter with another star. So that's not a good thing if you are looking for intelligent life on a planet that's going around some thing like a globular cluster there. There's just not going to be anybody to talk to there. Now, since that time, we've learned we've looked at better places, okay? So we're not doing that anymore. Okay, so here is, the irreversible antenna that has been used for SETI, and the Allen array up in northeastern California is another source done by the SETI Institute. So what are the things that we're looking for? Well, we're looking for signals that are not natural. And here's a picture of a unnatural type of signal. Also, it's got some natural signals in it too, which is down here. This is the noise, and this is just an instantaneous picture of what's going on with such a signal. We have a strong signal here, and then we have the noise down here. This is only instant in time. Another instant in time, you're going to have these guys shifted over or moved back and forth or something else. It's just, this sea of like a grass, it's sort of floating up and down, and, no rhyme or reason to it. But it is at a particular level. It's about, about minus 105 dBc, dB over K, is it? I've forgotten. But anyway, this signal is going to be there whether or not these guys change or not. This is the sort of thing that you would look for. Okay, so we also look for pulsed signals. This is a common way of putting information on it. This is sort of AM signals, if you will. And we could also look for FM signals. We could look for polarizations, because nature doesn't like to polarize stuff completely going from one polarization to another. It sort of drifts from one to another, okay? Yes, the sky is polarized, but it's polarized in sort of a continuous fashion. 90 degrees away from the sun, you see a lot of polarized signal, but it goes slowly. You get less polarization as you get closer to the sun. It doesn't turn on and off, and that's what I mean by a signal that's highly polarized. So you would turn it on to one polarization and then switch it to the other one. Okay. Alrighty. Now, now folks did find some signals that they thought was SETI induced. This is the antenna that they used. It's called the Big Ear, and in 1977 they found this signal. It's called the WOW signal because the signal is what is indicated here with the little circles here. Nominally, you would get nothing as evidenced by here, and this is from a teletype, type of printer. Now, 1 is sort of level of noise here, and you can see some 3s and 4s showing up. But then, what you would start with is the next signal up from nothing would be 0. And then you would get a 1, and then or a 2, and then a 3 and a 4, and then a 5, and there's a 6. And then after you get done with all the numbers, going up to 9, then you would start with letters, and then you go from A until you get to Z. And I've seen some indications of pictures where you'd start using punctuation marks. But the point with the WOW signal is look at all these guys here, a very high signal relative to the 1s or the 2s. Okay, now people have found out where this antenna was pointed when we got this signal. And here is the declination and right ascension for this. And we have looked at these regions several times since and have never discovered a signal. Now it's thought that what ended up happening was there was a comet that went through there. And this comet is called 266P/Christensen. And the theory is that this comet is going to reappear on January 25th, 2017. And there's another one, P/2008Y2, called Gibbs, and that's going to appear on January 7th of 2018. So if we see those comets, again on those dates, then the indication is that this signal, this WOW signal, is due to those 2 comets and not from some extraterrestrial intelligence, because we have never seen anything since. Kind of sad. Well, getting back to the difficulties of this thing, here are some of the problems. One of the things that I'm getting some of this information from is the Silicon Valley Astronomy Lecture Series. And if you're interested in things astronomical, especially on the cutting edge, spoken to by scientists doing that work, I want you to just listening to those lectures. They're very interesting in general. Although sometimes some scientists have better deliveries than others, so we're people too. Okay, so as far as this is concerned, where do you look and for how long do you look? And that is a difficulty. One of the problems is when we're listening to folks that are out there. Basically, they don't know where we're here, right? As I indicated before, we have been sending sort of unintentional signals out since the 1920s or the 1930s. And, when people are talking about the unintentional signals, the first thing you think about is I Love Lucy, in the 1950s. And so those signals have only gone out, 50, 60 light years, And only a few number of stars are in that regime that we would expect to be communicated with. And so, first of all, the signal has been out there since the 50s, so that's roughly 60 years ago. So only if we're expecting a return message immediately, that means we have to divide that number by a factor of 2. So that means only those civilizations that are out there out there close to us within 25 light years would be able to communicate with us. So, and those are only guys that know that we're here. All right, so if we're looking for somebody that doesn't know that we're here, then they're going to have to be just focusing on a star and sending information to that star for a moment at a time, and then go to another star and send information there, and then go to another third one and bounce around to all sorts of different, maybe likely planets or likely stars, and then repeat the process. Okay, so they dwell on a particular star for a while, and they go to another one, and then, maybe in a week or so, they come back and they dwell on that original star again. And they just go around and doing this thing until something happens. And in a sense, that's what we're doing. We dwell on a star and we listen, or we dwell on a star and we transmit, and we do that even less. And then we just keep on doing it. Now, there are some other things that you could do, which is, for example, this one. You could put a transmission antenna or, the signal source at the center of the Milky Way, right? Because everybody's going to look there. And when you do that, then you would need to send, quite a lot of power out to everything in order for, somebody to see it. So for us to see something hitting the Earth, then that signal from the center of the galaxy is going to have to be 5 times 10 to the 17th watts in order for us to detect it. It's going to cost a lot of money to do that. $100 billion a year in order to finance this thing so that you could send advertisements, for automobiles and the next Prozac or, the drug du jour. Okay, now there are other ideas as well having to do with detection or sending signals. And that's, again, these are coming from listening to the Silicon Valley Astronomy Lecture Series. And that is, if you're interested in detecting or you're worrying about building too many, then you build one antenna and then two, and then four. You basically are doubling this system every time you build these things, and presumably you're going to get better at building these things, so the cost will come down. So, you basically never run into the regime of building too many. And this one is kind of interesting. You have a supernova go off, and then you send a signal in the opposite direction because everybody's going to be looking at the supernova. And they're going to continue watching it until after it dies down, and then you send your signal, and then boom, it says, "Hi, I'm here, buy our cars." Eclipsing binaries have the same characteristic. You basically know when to look and where. And then another possibility is this. We could look in the anti-sun direction all year long. And what does that mean? Well, recall when we talked about the Kepler spacecraft and the transits of planets covering their sun. So basically, you're looking at, you have the Kepler spacecraft looking at a transit, and you've gotten all that information down for that planet. And you think that maybe there is some intelligent life on there. And so what you do is, during the transit, the next transit that they have, you have sent a signal such that it intercepts that planet just at the same time that the transit occurs. And so, obviously, you're expecting them to look away from the sun, okay, into deep space, and then they're basically going to catch your signal. That sounds pretty clever to me. But you need to know pretty accurately how far away that star is, okay? And then there's this other one talking about, you have these garden balls, and, they're all silvered and everything, and basically with the visible light, you can see all over, you can see the half of the world, right? And so the moon can represent a telescope like this for radio waves, and so we could see the entire universe except for, half. But obviously the sensitivity goes down. But, here are some other detection ideas, and people are playing with these things. And I guess the final thing is improvements are we're getting this for free. I don't understand why we're still getting this for, say, Moore's Law, which is this one here, but it seems to be continuing all the time. It hasn't abated for, for 50 years, getting a factor of 2 of improvement in performance for any, in cost and in effectiveness and things like that for computers every 18 months. It's just crazy. And then we also seeing antenna size improvements by a factor of 100 every 100 years. Okay, so the sensitivity is where it's at, and part of the sensitivity is looking at the channels associated with the signal. That's more in looking at modulation of the signal, and basically, if you have more channels looking at a site, then you have a better idea of what that site is actually doing. And so this is just telling you basically how many star systems have been observed during this period of time, and then this is correlated with with the number of star systems that we would number of civilizations that we would expect to have hit. If we, at our current rate of observation. So this is sort of tying in the Drake equation with our observations as well as our incidental communications. So 1 million contacts is what Carl Sagan would say, 1 million civilizations out there in the galaxy from the Drake equation. Isaac Asimov would say that there was 66,000 or 666,000, and Drake himself said 10,000. So the point with this chart is that we've been sending out I Love Lucy, and that's going out at a constant rate, and then we're also sending under signals out and looking at specific targets and being able to go out further and further because our sensitivity is improving. So basically, what this chart is saying is that if we don't see something by 2030, then, basically the whole Drake equation idea just doesn't work. That's what it basically boils down to. It'd be kind of fun, though, if it does work. Now, this chart here is kind of an interesting one. You can comment on it in a couple of different ways. One, it shows you the Moore law and how computations are getting quicker and faster, and computers are becoming more and more powerful all the time. And these computers can then be compared to life forms. And so the point being is that, sometime soon we're going to be able to buy a computer that has the capability of a human as far as computation is concerned. But that doesn't mean that the computer is smarter than us. It just means that it can make a computation faster than us, or do a program faster than us. Most computers are still linear sorts of devices, and humans, as you well know, are not linear almost in any fashion. But a thought could arise that is this, though, that artificial evolution is much faster than Darwinian evolution. And so we start with sending radio signals out to communicate, and then at some point we're going to send machines out to actually do the communication for us. Okay, now I'd be remiss if I didn't say that you could, if I didn't let you know that you could help. So there is this place here associated with UC Berkeley, and you could go and help them search for extraterrestrial intelligence. Basically, you allow your computer to be utilized when you're not using it. So enjoy. Now, this gets us to our last topic associated with life, and that is Fermi's paradox. And the basic idea is this: if there are so many civilizations out there, why haven't we seen them yet? And there is a story that I just heard a couple days ago that goes like this. Suppose you wanted to see megafauna in Africa, and you take a ship over there, and then you land on the coast of Africa, and then you go about 500, meters inland, and you don't see anything. You don't see any hippopotamuses or elephants or giraffes or things like that. And so you get back on your ship and you go back home and say, hey, I went to Africa. There was no elephants. There was no tigers. I mean, well, no tigers there anyway. But there was no giraffes and there was no hippopotamuses. Africa doesn't have those things. Currently, we're in that situation now when it comes to looking for extraterrestrial intelligence. But the problem still arises, though, is if you think that there are so many civilizations out there, why haven't they come and seen us? Now, there's some particular reasons why. It could be that, first of all, we could be the only ones. That we are alone, and life and civilization is much rarer than we have guessed. Now, so far, the Drake equation in this parameter is a guess. We don't have very much data yet. We have speculations about Mars. We are sending spacecraft out to Europa, maybe Enceladus and Titan. But we don't have anything definitive, and I'm not sure if we've gotten spectra from the exoplanets yet to tell us that there's water vapor or methane and oxygen in some locale out there. The other possibility is that civilizations are common, but interstellar travel is difficult, that our desire to explore is rare, or that civilizations destroy themselves. These are all possibilities, and as I said, none of them are very appealing, because it sort of implies that still we're by ourselves, and particularly the first one and the third one, it doesn't bode too well, because at some point our desire to explore is going to have to be stymied. And I don't know about you, but, well, if I can't go out into the mountains and go exploring and seeing new things, it get really dull. And then this last one about civilizations destroying themselves, it sort of seems like a waste, Well, and then there's the third possibility, which is that they are there and that they're watching us, and we'll meet them. And hopefully it doesn't boil down to this sort of activity from the day the Earth stood still, where they basically give us an ultimatum saying that you better get your act together, otherwise we're going to make sure that that you don't harm anybody else, which means they're going to blow up the planet. Now the question then arises as to what would happen if we do make contact. SETI.org, or the SETI Institute, has some information in that regard. They thought they had seen a signal not too long ago, and they didn't report it out to anybody. But the next day, the newscasters were all down on them, asking about their opinions and that sort of thing. So it isn't like this could be held as a secret. Information gets out and just gets all over everywhere. But let me remind you, though, that what we would expect is kind of unexpected. Those things that they would be able to do could seem like magic. That comes from Arthur C. Clarke's 3 laws. Basically 2 having to do with science taking place on the Earth. But the last one is the one I want to concentrate on here. And that is, any sufficiently advanced technology is indistinguishable from magic. So imagine yourself being transported back in time 100 years, 400 years, 1,000 years with the knowledge that you carry in your head. You would be able to predict things that would seem just unbelievable to the folks that you would run into. You might be indicated as a witch or a wizard, which would mean that you ought to be worrying about your health and safety. But if you were sufficiently adroit, maybe that wouldn't be a problem. But you talking to other folks, it would be magic. And your ability to manipulate nature would be magic. Now, I'm not talking about the Harry Potter things. I find, I enjoy watching the Harry Potter things as much as the next person. But I found it very interesting that in the storyline, and this is not a derogation of the author, but that this civilization of magicians or wizards and witches did not have an idea of how the magic occurred, and that they couldn't manipulate it in any understandable way. They were just as unknowledgeable or ignorant of their own magic as we would be, as Muggles would be. Okay, so that ends it for our discussion about life on other worlds. I'm sort of drawn to the first chart that we had where, we'd have some of these people coming in from some, in a flying saucer, and they're landing and they say something like, oh, nice to meet you. I want to talk to you about the kingdom of God. Anyway, I'm sort of related to that. Or as well as, oh, we want to have you guys build stuff for us because your labor costs are so much less. All right. So we'll talk to you later.